This video is an introduction to electrochemistry. So what's electrochemistry? Well, you might have guessed it has something to do with electricity and chemistry. And that's exactly right. Specifically, electrochemistry is about the relationship between chemical reactions and electricity. When we're studying electrochemistry, there are basically two main ways that chemical reactions and electricity interact. Here's the first one. Certain chemical reactions can create electricity. Okay, so that's what's going on in a battery. There are chemicals inside the battery, they react together making a chemical reaction, and that chemical reaction creates electricity. Okay, so that's the first way that these two things interact with each other. The second is that electricity can make certain chemical reactions happen that wouldn't happen otherwise. We'll look at examples of both of these situations. So if we're going to be talking about chemical reactions and electricity here, let's just take a minute to explain what these two things are so we can know what we're dealing with. First off, electricity. What is it? Well, in really simple terms, electricity is just movement of electrons. I got a bunch of electrons in this diagram. They're moving in this direction, so I have electricity. Often when we talk about electricity, we're talking about movement of electrons through something. So maybe it's through a wire, or through a light bulb, or through a battery, or something like that. But if you've got electrons moving, you've got electricity. So if electricity is about moving electrons, that means the chemical reactions that we're going to be talking about are also going to involve movement of electrons. And that means that these chemical reactions that we're going to be discussing will tend to be oxidation-reduction reactions, because these are chemical reactions where electrons move between atoms. Okay, so here's how these two scenarios come into play. We can use electrons moving between atoms in an oxidation-reduction reaction to make electricity. The electrons are moving, so there's our electricity. And then for this situation, we can use electricity to force electrons to move between atoms to make oxidation-reduction reactions happen. Let's look at how that would work. So here I've got an oxidation-reduction reaction where electrons are moving from A to B. How can I use this to create electricity like along a wire? Well, what we could do is we could separate A and B, right? We know that electrons want to move from A to B, so if we separate them with a wire, then that means that the electrons moving between these atoms will have to travel through the wire, be moving through that wire, and bam, we've got electricity. Okay, now let's look at this example. Okay, let's imagine we have another oxidation-reduction reaction, electrons transferring from C to D. But imagine this doesn't normally happen because C doesn't want to give up electrons and D doesn't want to gain them. Okay? Here's where we can use electricity. Okay? We can take the electrical energy from a battery and use that to pull the electron from C here and to push them to D. Okay, so even if this reaction, the movement of electrons, doesn't normally happen, we can use electricity, we can use the electrical energy of this battery to pull and push the electrons to make this reaction happen. Okay, so this is kind of a broad, big picture overview of electrochemistry. Now I want to show you two examples of these situations, one where we're using a chemical reaction to create electricity, and one where we're using electricity to make a chemical reaction happen. So here's how chemical reactions can create electricity. And to do this, to make electricity using chemical reactions, we often use a device called a galvanic or a voltaic cell. I've drawn one right here. The version that I've drawn uses zinc and copper metals. So let's take a look at the chemical reaction that's happening in this galvanic cell that is what's creating electricity. So here's a chemical reaction. We said that that galvanic cell used zinc and copper. So if you take a neutral zinc atom and put it near a copper 2+ ion, electrons naturally move from the zinc atom to the copper. And so what happens there is the zinc takes on a 2+ charge because it loses 2 electrons, and the copper becomes neutral because it gained 2 electrons. So why does this happen? Well, it happens because there's kind of a tug of war between these atoms. Cu2 plus has a strong pull for electrons, and zinc, Zn, has a weaker pull for electrons. And that's why the electrons move. We can describe how they move in terms of oxidation and reduction. Zinc over here is losing electrons, so it is oxidized. Cu2 plus is gaining electrons, so it's reduced. Now, the most important thing about this process is that it happens on its own. All you got to do is put neutral zinc near copper 2 plus, and the electrons just naturally move. It happens on its own. This is a process that we can call spontaneous. It's spontaneous. It just happens on its own. Now, a really common question, that's a great question, is people say, okay, yeah, but like, how do you actually know that the electrons are going to move from zinc to copper? How do you know that copper has a stronger pull for electrons? Well, you can look it up. There is this chart that we'll be using a lot in electrochemistry that's called the standard reduction potentials. And it lists elements and compounds in terms of how strongly they want to pull electrons. So the higher you go up here, the more these elements want to pull electrons towards them. So we got copper 2 plus up here, and we got zinc down here. So the way this chart works is if copper is up here, if it's above zinc down here, then copper is going to be stealing electrons from zinc. Copper is going to have a stronger pull. So that's how we know that copper is normally going to be pulling electrons from zinc, and that this reaction is just going to happen on its own. So this reaction, as we said, is what's going on in a galvanic cell. So let's see how we can use this galvanic cell to create electricity from this reaction. Okay? Well, we said that zinc is going to be giving electrons to Cu2 plus. But when these atoms just give electrons to each other just like that, it doesn't really create electricity that's very useful for us. But if we can separate the zinc and the copper 2 plus, then we can make the electrons travel through a wire in order for them to move. And that is exactly what we do in this galvanic cell. Okay, check this out. We got zinc here in this container, and then we got a whole bunch of Cu2 plus in this container. There's also Zn2 plus here, but it's not really that important. So what happens is the electrons want to get from this zinc to this Cu2 plus, but in order to do that, they've got to go through this wire. So this is the path that the electrons take. They're moving through this wire to get from the Zn to the Cu2 plus, and check it out. They're moving along this wire, which means that they are creating electricity. They go into this piece of copper, and then they move here wanting to get to the Cu2 plus. So we got electrons moving in this direction, and as I showed earlier, we can even take a light bulb or something and put it between here, and the light bulb will light up because there's electricity moving through this wire as the electrons naturally, spontaneously move from the zinc to the copper. All right? Now, in electrochemistry, we often want to describe what is happening in a device like this using oxidation and reduction. We want to be able to talk about the different parts of a galvanic or voltaic cell and say what's happening to them with electrons. So here are just a couple words that we'll need to know. These two pieces of metal, the zinc and the copper, are called electrodes. The electrons are going into the electrode and coming out of the electrode. And now we can name these electrodes based on whether oxidation or reduction is happening there. Okay, here are two words that we use all the time in electrochemistry. The anode is where oxidation happens, and the cathode is where reduction happens. So let's look at what's going on here. Okay, we got zinc. What's going on with the zinc? Well, we know that zinc is losing electrons. It's being oxidized because the electrons are moving out of the zinc to get over here to the Cu2 plus. So the zinc is losing electrons, it's oxidized, which means that the piece of zinc here is the anode, the place where oxidation is happening. Over here, the copper is where electrons are getting added to the Cu2+. So the piece of copper as an electrode is the cathode. It's where reduction, it's where gain of electrons is happening. So the zinc is the anode because it's a site of oxidation. The piece of copper is the cathode because it's the site of reduction. So this is how a galvanic cell uses a spontaneous chemical reaction that happens on its own to create electricity. Okay, so anode, cathode, how are you going to remember them? Well, this is a really easy mnemonic, a way to remember it, okay? It's kind of like thinking about two animals, okay? An ox, red cat. Just remember that right now, okay? It stands for anode is the site of oxidation, an ox. Red cat stands for reduction happens at the cathode. An ox, red cat, learn it right at the top of your tests. You'll never mix these things up again. Now, let's look at how we can use electricity to make certain chemical reactions happen that wouldn't happen otherwise. Using electricity to make chemical reactions happen is a process called electrolysis. We do electrolysis in a device called an electrolytic cell. I got a diagram of one of these here. And in our example, we're going to see how we can use electrolysis in an electrolytic cell to take water and split it apart into hydrogen gas and oxygen gas. So just like the reaction we saw earlier with zinc and copper, this is also an oxidation reduction reaction. We got electrons moving here. To understand how they move, we got to take a look at the oxidation numbers for the different elements here. Hydrogen's oxidation number is going down, which means that it is gaining electrons. It is reduced. Oxygen's oxidation number is going up, which means that it is losing electrons. It is getting oxidized. So we can kind of sum up what's going on here with a diagram like this. Electrons are moving from oxygen, which is losing them, to hydrogen, which is gaining them. But this is a problem, okay? It's a problem because it goes against what oxygen and hydrogen normally do with their electrons, okay? Oxygen has a stronger pull for electrons, and hydrogen has a weaker pull for electrons. So if it could, oxygen would want to take electrons from hydrogen, and hydrogen kind of would be willing to lose them. But for this reaction to happen, we're asking that the opposite take place, okay? Oxygen is usually stronger, but we're asking it to give up electrons. Hydrogen is usually weaker. It usually loses electrons, but here we're asking for hydrogen to gain electrons. And we can look again at this list of standard reduction potentials just to see who's stronger and who's weaker, all right? Oxygen is up here. The further up you are, the stronger pull you have for electrons. Hydrogen is all the way down here, so you can see that oxygen really wants to take electrons from hydrogen. But instead, we're asking oxygen to give electrons to hydrogen, okay? So based on that information, this is a reaction that doesn't happen on its own because oxygen doesn't want to give up these electrons. So we can say that it is not spontaneous. It's not going to happen on its own. We're going to have to use electricity to make it happen. And it turns out that a battery, the electrical energy from a battery, can pull the electrons from oxygen and push them to hydrogen. It can force this reaction to happen. Here's how. So we can make this process happen by using an electrolytic cell. This is some water here that we want to break down. We've got these electrodes, and the electrodes are connected to a battery. Okay, so normally oxygen has a stronger pull for electrons, but we can use the strength of the battery to pull electrons away from oxygen. Okay? Here, hydrogen would normally give up electrons, but we can use the battery to push electrons to hydrogen. In terms of oxidation and reduction, this means that oxygen is losing electrons, so it is getting oxidized. Hydrogen is gaining electrons, so it is getting reduced. These electrons are getting pushed to it from the battery. Okay? So what about anodes and cathodes? Remember, anox, red cat. Anode is where oxidation happens. So over here is the anode, the site of oxidation, where oxygen is losing electrons. And over here is the cathode, where hydrogen is getting reduced. So this is how electrolysis happens. We force the electrons to leave oxygen and we push them into hydrogen, making this process happen using a device like this called an electrolytic cell. So that's an introduction to electrochemistry. We looked at the two ways that chemical reactions and electricity interact. Certain chemical reactions, those that happen on their own, those that are spontaneous, can create electricity. In order for that to happen, we separate the two things that electrons are moving between, and we put a wire in between them so the electrons will move through the wire. Electricity can make certain chemical reactions happen that wouldn't happen otherwise if a certain atom doesn't want to give up electrons or another atom doesn't want to gain them. We can use the electrical energy from a battery to pull electrons and to push them, forcing oxidation reduction reactions like this to happen. We looked at how galvanic or voltaic cells use processes like these, and we talked about the electrolysis process of breaking down H2O, water, into H2 and O2. So that's a good example of this.